The next proof I want to show you is one of my favorite proof techniques, one of my favorite proofs, and that is a false proof. And we're going to see a lot of these during the term too. And if we could bring the screens down, somebody back there to, yeah, great. Bring the screens down. And then turn this on for me. So I'm going to prove to you that 90 is bigger than 92. All right, and that hopefully is not really true. But watch this proof and see if you can see any problems with it. All right, the proof by PowerPoint. Right away, you should be suspicious. I'm going to take two triangles with total area 90 and put them together and then divide them up into four triangles with area greater than 92. And by the conservation of area axiom, which you want to be maybe thinking about, this will imply an area of 90 is larger than an area of 92, and therefore that 90 is bigger than 92. All right, those are my triangles. They are right triangles, 9 by 10. If I put them together, I get a 9 by 10 rectangle. Of course, it has area 90, 9 times 10. Now I'm going to slide these triangles across their diagonal so that I get, instead of having 10 on the side, I'm going to slide it so I get a 2 and an 8. Okay? I had 10 there before, now it's 2 and 8. And then you see I've got this, I kind of cut off along the dotted line. And as you can see, that dotted line, won't compute it exactly, but it's a little bit bigger than 2. Right, it's a little bit longer than that 2 there. You can see that. All right, so I'll call it 2 plus, bigger than 2. Now I slice off along the dotted line. And now I'm going to put those two triangles together, and I create a rectangle, 2 by 2, a little more than 2. Now the area of the little rectangle is bigger than 4, because I got 2 times something bigger than 2. And you can see here I have the 8 left over, and I have 9 plus 2 plus means it's a little bit bigger than 11 by 8. I got area bigger than 88. Add them up. I got area bigger than 92. So I started with 90, and I created more than 92. All right, what's the problem here? I mean, this would be good if I could do it. I'd get some gold, bars of gold and, cut them up and do the game, and I'd make more gold. That would be pretty good if I could do that. Is it the conservation of area axiom? Did I assume something there that was too powerful, that if I manipulate the area of rectangles like this, that the area needs to be the same? Yeah? My bigger ones aren't closed. Well, let's see. I don't know. Let's go back and see how I made those bigger ones. All right, I got my triangles, right? I'm just chopping along the line there, and I got 2 plus and 9. Those are rectangles. They look like rectangles. Yeah, yeah. Well, it looks bigger than 2, doesn't it? Yeah, 2 plus is, well, bigger than 2 is bigger than 2, but yeah, maybe that should have been a 2 minus. Would that change anything? Yeah, if that had been a 2 minus, then we'd have area less than 4, area less than 88, and then 90 would be less than 92. That would be okay. But it sure as heck looks bigger than, the 2 plus looks bigger than the 2, doesn't it? I don't know. Do they got distortion out there? I guarantee you, if I measured on my screen, that 2 plus is bigger than the length of the 2. I guarantee you. We can take a ruler on my screen, and the 2 plus will be longer on the ruler than the 2. That I guarantee you, but you're on the right track. Yeah?
That 2 plus is really 1.8.
Good. All right. Now, how did you... But it is true if I measure it on my screen, it's bigger. Yeah?
So are the triangles, like, drawn to scale? It's like on
No.
the SAT, they always say not to scale, right?
Yeah. Yeah, they're not drawn to scale. In fact, if I go back to the beginning, it says 9 by 10. But in fact, if I measure the 9, it's bigger than the 10. All right? So this is one of the big problems of proofs by picture. Because looking at it, you're not thinking which is bigger, 9 or 10 up there. The 10's bigger, even though it's not. It's shorter. But when you get down into the proof, well, clearly the 2 plus was bigger than the 2, because it looks that way. It is on the paper. All right? In fact, if you go computer, you're probably right. It's 1.8, not 2 plus. But that's how the error crept in and how it was drawn. And then you're going along with the proof, and everything else is just fine. So the mistake is right up front. I drew it wrong. Okay? And this happens, you're doing graph, we'll talk about graph theory in a couple weeks, over and over again, people do this. They draw it, it looks like this, you accept that, and then you're dead. Everything else, there's no hope. Everybody clear what went wrong in this picture? How we got off track? This is sort of a nasty one. Okay. Now, one of the nice things about proofs is that when there is a bug, if you really write it out step by step, and there's a bug, you can go back and find it. And so this, I didn't sort of really write it out very well step by step, and it was harder to find. Now, all right, so if we can pull the screens up. Thanks. OK, so for the rest of today and the rest of this week, we're going to talk about a different kind of proof technique, which is induction. Now, induction is by far the most powerful and commonly used proof technique in computer science. If there's one thing that you should know by the time you're done with this class, it's how to do a proof by induction. In fact, if there's one thing you will know by the time we're done with this class, is how to do a proof by induction. And in some sense, when we get to grading the final, how we measure ourselves as instructors, the first test is, can you do the proof by induction question and do a good proof there? You will see it on the midterm and the final, probably in multiple instances. Now, just to make sure you become intimately familiar with induction, we're going to do over a dozen proofs with induction in class and many more in homework over the next 5 to 6 weeks. You'll probably be dreaming about induction if we're successful here soon. The good news is that induction is very easy. Once you get your mind around it and get some practice, it really is not a hard thing. In fact, induction is really just an axiom. So let me state it. Let Pn be a predicate. If P of 0 is true, and for all natural numbers n, P of n implies P of n plus 1 is true. So here I'm saying that this is true for all n. Okay. Then, for all n natural numbers, P of n is true. All right, another way of saying this without the for alls there is that if P0 is true, if P0 implies P1 is true, if P1 implies P2 is true, and so on forever, then P of n is true for all n. So then P0, P1, P2 forever are true. Okay? Now, you can sort of see why this is a reasonable axiom. Because if P0 is true, and P0 implies P1, then by that modus ponens thing, or one of the logical deductions, we know P1 is true. And if P1 is true, and P1 implies P2 is true, then we know by the same reasoning P2 is true. And so on forever. Now, the reason it becomes an axiom is that and so on forever part of it. That's why we need it as an axiom. You can sort of view this as a series of dominoes. You know, I got a domino for each n. And each domino knocks over the next in terms of truth. Knocking over corresponds to truth here. And if I know P0 is true, that means I knock over P0. P0 implies P1 means P1 goes down. P1 implies P2 means P2 goes down, and so forth. All right, pretty basic. Raise your hand if you think you don't have a lot of experience with induction. All right, yeah, that's pretty typical. About a third to a half of you. So we're gonna change that.